All right. So last day we were in section 2.3, and so just as a kind of a quick review here, we talked about functions that are increasing and decreasing and how we kind of can, and that's why I brought this one in here so we can have a look at kind of decreasing and then increasing and then decreasing. Increasing and decreasing, if you just kind of trust your gut and just kind of think, okay, well, if it's going down, then it's decreasing, and if it's going up, then it's increasing. Then you kind of have the hang of increasing and decreasing. So it's not that crazy. I'll kind of scooch that down there for a little bit. So we talked about increasing, which means it's kind of going up like this, and decreasing functions, which means they're kind of going down like this. We're going to do that. Oops, it's not a bullet. We talked about global max and mins, so maximum and minimums. Global max and mins are kind of overall max and mins. So if we look at a graph here, right, like here's a minimum and here's a minimum, and then here's a maximum, right? We see that these tails keep going higher than that maximum. So that's what makes it a local maximum, and this is a local minimum, and this is a global minimum. The difference is the global minimum is the overall max or min. So the global max or min are overall maximums or minimums. Global max and mins, endpoints can be global max and mins. So endpoints are kind of, oops, missing an N there. Endpoints, and probably a D too, I can't remember. Endpoints are kind of particular because in order to be a local max or min, which we haven't mentioned here yet, but in order to be a local max or min, then we have to have it as the smallest point around all the neighboring points. So that's what makes the endpoint kind of hard, because if we say that, let's pretend that this graph ends here, it doesn't, it extends to infinity, but let's say it were to end here, then yes, coming in from the left, it's the highest point. If it's the end point here, then it would be the highest point, but there's nothing to compare it to on the other side. And so we can't know if it's the local max or min. So endpoints can be global max or min. For local max or min, our points, let's see, are points that are the smallest or largest or kind of the most extreme in either direction compared to its neighboring points. So the largest, I should match them up, the largest or smallest outputs in, now the textbook does a good job. They've got this little blurb. Let me just grab it here so we can move on. Where is it? Oh, now I can't see it here. But anyways, so the local max and min is essentially where it changes from maximum to minimum. So let's say that instead, or increasing to decreasing. Man, hopefully you're just as sleepy as I am. I've been up for a long time, but I don't know. The local max or min is where a function changes from increasing to decreasing or vice versa. From increasing to decreasing or vice versa. Right, so imagine you've got something like, move this down a little bit here. Move it down a little bit more. Let's say you've got a graph like this. Your x, y axis, oops, that's a y. Let's say you've got something that looks like this. Right, so here we know this is a maximum, so just in general, a maximum here is going to be where it changes from increasing to decreasing. And so here it's going to be increasing and then it switches to decreasing. You probably would have picked this as a maximum anyways, right? But we don't usually think of it as, oh, okay, it's the point of where it switches from increasing to decreasing. We just think of it as the highest point or the lowest point, of course, if it's a minimum. All right. Whereas if you have something like this here, this might be a minimum, might be a local minimum, right? If you have something like this, let's say you have something like this, this is also a minimum, okay? Because this minimum over here on the right-hand side is larger than, or sorry, yeah, higher, let's say, than the minimum over here on the left-hand side. This we could call a global minimum, assuming it ended here. So let's just end this graph here and here, okay? So here, this would be a global minimum because it's the overall minimum. This would be a local minimum, okay? We've got 3 maximums, right? So 1, 2, 3. This is then the end point, right? And so this is a global maximum because it's the highest possible point. End points aren't allowed to be local minimums or maximums. So this is our maximum here, and this is our global max. So here, this is a local maximum, and this is a global maximum. And here, I'll change this to be a local minimum and a global minimum. And we're not talking about this one because it's not the overall maximum, and an endpoint can't be a local maximum. So we leave it out. So let's talk about, let's make this a little bit bigger. I just wanted to have some graphs ready for us to talk about. So what we're going to do is we're going to talk about the intervals where this thing is, we're going to find the local max and mins, and then we're going to find the value of x where this happens. So we're going to find the actual point where this happens. And then we're going to be talking about which intervals are they increasing and decreasing on. Okay. So for the increasing and decreasing those intervals, it's not going to include the maximum on either end. because at the maximum, the slope is actually 0. So, and we use that to our advantage later in calculus. So, so just keep that in mind, that the endpoints or the maximum and minimums are not included in the increasing and decreasing intervals. Otherwise, it can be hard. Which one is it included in? So if we talk about, let's just look at 43 here. Oh, weird number, but that's okay. So what we're going to do is, well, it establishes the axes here. So each square is worth 1. And so first, let's pick out our maximums. So here we've got a max. And this maximum, right, seems to be a local maximum. Remember this, I said, because the arms kind of extend forever, it's implied that this graph just kind of is pointing up very much like a parabola, right? And so it's pointing up, and it's, we can kind of imagine these things going on and on forever. Okay, so this is going to be a local maximum because there are points that are higher than it, right? And so here, this is our local max, and the local max is at what point? X is 0 and Y is 2. So 0, 2. Okay. Looking at the overall behavior of this graph, it seems like it's going up, up, up. Let me just shove a little bookmark in there. Not holding the pages, hands free. So it looks like things are going up, 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 and this minimum seems to be an overall minimum for this whole thing, so making it a global minimum. So we'll specify that. We could call them local minimums. There's no harm in that because neither of these are endpoints. And so this is a minimum, this is a minimum. I'm going to call this a global minimum and this a local minimum. Okay, so let's use a different color here. So here we have a global minimum. If you wanted to call it a local minimum, that's totally fine. The local is just saying, well, in relation to, so local to x equals 2, it's a minimum, right? Overall, it's not necessarily a minimum, right? There are tons of points that are less than that value down here. But in relation to other outputs around x equals 2, it's a local minimum. And so that's where that comes from. And so the global min is at -1, 2, and -1. And we've got this local minimum. The local minimum is at 2, 0. Okay. Let's find where it's increasing and where it's decreasing. So just looking here, it's decreasing, and then it switches to increasing, and then it switches to decreasing, and then it switches to increasing. So let's talk about just moving from left to right on the graph, right? We've got this kind of, this is decreasing, and then here it's decreasing. Decreasing. Now this is, so we're talking about where on x is it increasing and decreasing. So it's decreasing from -infinity up until x equals -2, right, where we reach this minimum. So from -infinity up to -2, not including -2, right, that's the turning point. So, and then we pick it right back up at x equals 0, going to x equals 2. So union 0, 2. Okay. Running out of colors here. Purple. Where is it increasing? Here and here. So it's increasing, looks like from -2 up to x equals 0. Notice that it's going to fill in the gaps here and extend beyond 2 later, right? And so it has to either be increasing or decreasing. So unless it's a perfectly flat horizontal line, then it's neither. From x equals 2 to positive infinity, it's also increasing. Okay. So you can go ahead, you can do these with the rest of these, but I think we all have the hang of it, hopefully. Okay. All right, so now I want to switch here. I think. Any questions before we keep going?
I might not have been paying as much attention as I should, but is there a particular reason why? Well, okay, why it's like curved brackets on some of these as opposed to square brackets?
So we use curved brackets because at these points, at the minimums and the maximums, the slope is actually 0. So it's not increasing or decreasing. So it's decreasing up until that point, but not including that point.
Okay.
And
okay,
then
I see.
same for the increasing.
All right.
Cool.
I think I get it.
Nice. All right. So we kind of skip ahead a little bit. So for section 2.4, it's on average rate of change. It's really just the slope between 2 points. And so that's all Shaun has me say here, so that's good. And then we've already talked about linear functions, or we haven't, but you guys have with Shaun, so we're skipping that section as well, right into section 2.6, which is on transformations of functions. But I do want to make a note about skipping ahead through that, so when you're looking through these notes, it's not confusing. So 2.4 is on the average rate of change of a function okay. So the average rate of change of a function between x equals a and x equals b of a function between x equals a and x equals b is the slope between these 2 points. Is the slope between these 2 points. And that's where we're just going to leave it. Okay. 2.5, I'll just make a note here, is on linear functions and models. Linear functions and models. But this was covered, I'll say, covered in chapter 1. So we're not going to cover it here again. Covered in chapter 1. Putting us at 2.6. Just steaming through here. Transformations of functions. Transformations of functions. So the idea with the transformation of functions is that you start with your core function. And remember last day, where were we here? Last day we talked about where these functions, right? These core functions, and I said it'll be really useful to memorize these general shapes, right? So that we know when we're transforming this thing. So what we do is, if the core function can be boiled down to x to the power of 2, for example, then you know your initial shape, and then we can transform it from there. Okay, so what we mean is we'll start with vertical shifting. So vertical is up and down, right? And then we can talk about horizontal shifting. And then we can stretch this thing. We can reflect it around the X or the Y axis. And what I want to do is, I'm going to cheat a little bit and hopefully it's okay. Remember, I post these notes on Moodle right after class. So you have access to these, so don't worry. But what I'm gonna do is I want to, where is it? Functions part 2. I want to cheat and bring in just these little summary blurbs, just so we can talk about them instead of just writing out all that stuff like crazy. Okay, so first thing we're going to do is, if we have a function f of x, and we're just always going to assume that c is greater than 0, you'll see c comes up kind of as a general value that we're using when we're talking about transformations. And so if we have f of x plus c, well, what that means is you're going to shift the graph of f of x upwards c units. So if you see something like x to the power of 2, right? So say, oops, say we want to graph x to the power of 2 plus 3, what do? Well, we take the graph of x to the power of 2 and we move it up 3 units. Okay, so every point on x to the power of 2 is going to get bumped up 3 units. Move the graph of x to the power of 2 up 3 units. Okay. Same thing if you have f of x minus c, then it moves it down c units. Okay. And so it's got this handy little, so the blue is the original graph f of x, and then you figure out if you have to move it up or down c units. So vertically, so up and down, graphs behave the way that you kind of want them to, assume they will. Whereas horizontally, I actually find that they behave opposite of how I want them to, and that's always kind of hard for me. So I don't know, maybe you have it under control. But if we talk about horizontal shifts, and let me go in here and do a little scribble so it bumps it to the top. How about that? Okay. So like I said, I post these notes right after class on Moodle, so you'll have them. Because I just want to cover all these facts so that we can actually do some problems. And this is such a short class. It's like blink and you miss it. I know you don't feel like that, but I do. I'm used to having an hour and 50 minutes in my other classes.
Don't worry, this was a lot of the time. I'm like, hey, yeah, it's test time now. We're putting it here.
Yeah, totally. It's like, hey, what's going on? All right, so like I said, vertically, things kind of behave the way you want them to. Horizontally, I don't know. For me, it's the opposite of how I think it's going to be. So if I have, so notice that the C is now acting on the X, right? Whereas here, the C is acting on the F of X. So the C is acting on the Y. So that's what makes it vertical. Okay, so I'll make a note here. Notice the C is acting, I'll say acting on F of X. F of X is Y, right? Which is why you have a vertical shift. Which is why the shift is vertical. Oops. Okay. Here, I'm going to squish this together, but I do have a page break here, so I'm just kind of taking advantage of that. If the C is acting on X, right? So here, like this, F of X minus C, so then I think of it as acting on the X, then the shift is going to be horizontal. Then the shift will be horizontal. Okay. So now I'll put that there. Let's talk about it. So when I do X minus C, I don't know about you guys, but if I do X minus C, I always want to put it to the left. But it actually shifts the graph to the right C units. And that's what I mean. It kind of has the opposite effect. But as long as I remember that if the C is acting on the X and not F of X, it's going to be the opposite of what I want to do. That's a good kind of memory cue for me, at least. So you'll have to figure out what works for you to remember that, okay, it's actually moving to the right if you're subtracting C. And maybe you have the kind of brain where you just say, well, yeah, that makes sense. I don't, but you just need to remember these things. Okay. So what we can do, we can combine vertical and horizontal shifts. So we can combine vertical and horizontal shifts to have something like this. Okay. So what we start with, let's say overall, so if the end goal is to graph something like the root of X minus 3 plus 4, what you do is, and I'll move this over here, okay, and I'll just outline it. To graph F of X is the root of X minus 3 and then plus 4, what you do is you identify the core function, which is root X. Root X is what's been manipulated, and that's when it's really useful to know what root X looks like. So root X looks like this. Okay. So then what we do is we use the order of operations. So just like you would work through an algebra problem, you would work through from the brackets and move your way out, right? Just kind of like an onion, bloom out. So here, you'd have to apply the X minus 3 shift first, right? X minus 3 is a horizontal shift to the right 3 units, right? And so what you do is you take this graph and you shift it over to the right by 3 units. What's the easiest way to do this is to pick maybe 1 or 2 or 3 points not just one. Do 2 or 3 points. Shouldn't have said one. Figure out what 3 points are. 3 is good. On the original graph, and then apply the -3 to each of those x's and figure out what your y is, right? And so, so you do the x -3 shift first, and then to that graph, you can move it up 4 units vertically, right? And so the first step here is 1, identify the core function, right? Which in this case is root x. Okay. You can pick some points, some values of x on root x. Let's make that point number 2 or step number 2. Pick 3 points on f of x equals root x to follow, right, through the transformations. Through the transformations. Okay, so you can pick x equals 0, that's a nice one, right? 0, 0 is a point on here. 1, the square root of 1 is 1. The square root of 4 is 2. I'm picking convenient values of x. So in this case, we can use 0, 0, 1, 1, and 4, 2, right? If x is 4, y is 2, right? The root of x. So then, first thing you're going to do is you're going to work your way out from the core function, right? So if you're manipulating x, then you have to do that first. Okay, and so for each x now, right, you want to do x -3 and then square root it. All of these, so x -3 says we have to move to the right 3 units. I always get confused. 3 from the core function, root x, apply the transformations working your way out. Okay. So in this case, right, root x -3, we would plot those points first. So in this case, whoops, 4. Shift f of x equals root x to the right by 3 units. Okay. So what happens is each value of x, you add 3, okay? And so 3, 0, that's on here, right? So now you have 3, 0, 4, 1, and 7, 2. Okay, and we can check 3, 0, 4, 1 looks about right. And then 4, 5, 6, 7, 2 looks about right, right? So if you had to graph this, obviously I've given you the graph already, but that's what you would do, and you would just shift everything over and you can just redraw those graphs. So picking 3 points that you like initially, this one, and this one, right, is going to shift over to 1, 2, and 3, 4, 5, 6, 7. There. Gosh, I'm not very good at 4, 5, 6, 7. Try that. Okay. Notice that here, this point has just moved over 3 units if I had drawn on a straight line, but I haven't. Okay. So then if we're working our way out, okay, x minus 3, so we've graphed the root of x minus 3. So then what we can do is we can apply the plus 4. So for each y, vertically it behaves the way we want it to. So for each y, we're just going to add 4. So 3, 0 becomes 3, 4, right? 4, 1 becomes 8, 1. Or sorry, 4, 5. And 7, 2 becomes 7, 6. Okay. Now move f of x equals root x minus 3 up 4 units by adding 4 to each y. Okay, so the resulting points, you have 3, 4, 4, 5, I said. Why am I struggling with that one so much? And 7, 6. Okay. So this procedure of first identifying the core function and then applying the transformations, just kind of blooming your way out, that's going to be how you graph these things in general, right? So you don't want to try to tackle this whole thing. You want to break it down into a core function, find some key points that you can follow around, and then you can move those points around, knowing how the x minus 3, for example, knowing that it moves it over to the right by 3, and then adding 4 to f of x bumps it up by 4. Okay, so those are our vertical shifts and horizontal shifts. We can also do stretching, either horizontally stretching or shrinking, or vertically stretching or shrinking. So I'm going to bring those little cheat sheets into. Oh, I forgot about reflecting the graph. Let's throw that in there too. Why not? No, it's important. So before we get to shrinking and stretching, I did those opposite. If you have the negative, so if you're negating the function itself, f of x, so notice that this is the negative of the y, then you reflect around the x-axis, right? Notice that if you're reflecting around the x-axis, well, this y value, this positive y, becomes a negative y, right? Which is exactly what you're doing here, okay? If the negative is on the x, right, then you reflect around the y-axis, right? So this positive value of x becomes a negative value of x. So it's a little bit weird that it would, so if you negate the y, it switches around the x-axis, but if you think about, okay, a positive y becomes a negative y, well, the only way for that to happen is to revolve around the x-axis. Same thing, if a positive x becomes a negative x, then you have to revolve around the y-axis. Okay. So now let's talk shrinking, and once we have this toolkit, we can kind of combine all these things and transform huge graphs. Okay, so let's talk about vertical stretching. Okay, and shrinking. So let's say you have c times f of x. Notice that the c is manipulating the function f of x, which is c is manipulating the y, right? And so again, if c is larger than 1, then we expect it to stretch out, right? Because we're stretching our y. If we have c is 2, for example, then our y goes from 1 to 2, right? So I would say that vertically, again, for stretching and shrinking, if you're multiplying by some value of c larger than 1, then you stretch the graph. And then if I tell you, okay, now y is going to be 1/2 y, well, then you shrink it down, right, by 1/2. So I feel like, again, vertically, if things are being applied to the function, it behaves the way you think it will, right? So notice c is acting on f of x. Okay, so that's what makes it vertical. Okay. How about the horizontals? Horizontal shrinking and stretching. So now notice that the c is acting on the x, right, inside f of x, okay? And this is where it gets a little bit weird, again, because it's horizontal, right? So as soon as it's acting on the x, we need to kind of put a stop on it and say, okay, there's something weird that happens here, and maybe flip back through your notes and make sure you've got it right, right? So if c is greater than 1, so if I have f of 2x, for example, then we actually shrink the graph horizontally by a factor of 1/c. That's weird, right? But let's just talk about it. So if you have f of 2x, right, then what happens is you're going to shrink it horizontally. So shrink it horizontally like this, like an accordion, by a factor of 1/c. So by a factor of 1/2, if we're talking about c equals 2, for example. Okay, whereas if c is between 0 and 1, then it stretches this graph horizontally by a factor of 1/c. But if c is between 0 and 1, so let's say 1/2, 1/1/2 is 2, so it stretches it out. Okay? This one, I've got some space here, so I may as well fill it. When we manipulate x by cx, or sorry, by x, as in f of cx, the graph is changed horizontally, right? Is changed horizontally. Okay, but not really in the way you think. Okay, but oops. But be careful, because it might not behave the way you think. The way you think it will. Okay, so here, it's going to be on the next page, but still. Okay, so if c is greater than 1, then we shrink it horizontally by a factor of 1/c. Okay, so let's say let c equal 2, right, then f of 2x says shrink the graph horizontally by 1 over c, which is 1 over 2. So shrink it by 1/2. Okay. Whereas if c is between 0 and 1, so let's say c is 1/2, let c be 1/2, then f of 1/2 x says stretch the graph horizontally by 1 over c, which is 1 over 1/2, which is 2, right? A fraction over a fraction. 1 is 1 over 1. 1 over 1 over 1 over 2. Ugh. Flip and multiply. You get 2 over 1. And I'll write that here, which is 2. Right, so you want to be really careful. As soon as you're making changes to the x value and not the f of x overall, it's going to be a little bit sneaky. Okay. The last thing I want to end up on, and then I'm not sure if I'm meeting with you on Monday or if Shaun's going to be able to come back on Monday. But what I want to do, I just want to introduce the idea of even and odd functions, and then we can pick up on some examples next day. Okay. So, because I know I'm already out of time here. Okay, so if you have a function, then as a rule, f is even if you're able to take negative x and manipulate it, so algebraically manipulate, replace all the x's with negative x, and then you're able to kind of undo it, and it looks the same as f of x for all the x's in the domain of f. F is an odd function if you apply negative x inside the whole function. So you replace all your x's with negative x, and you're able to manipulate it to look like negative f of x, right? And then there's so an even function just kind of has this symmetry around the y-axis, whereas an odd function is symmetric with respect to the origin, which is a little bit weird. But if you think about, in general, x to the power of 2, we call it an even function because it's a power of 2, right? It's got this symmetry around the y-axis. X to the power of 3, now it helps to know the general shape of x to the power of 3, while it's got this symmetry around the origin. So I'll leave it there. And how about this? I'll put some problems in here. How about, just so you have something to work on, and what you can do, just so you have them in the notes, okay, you can try some of these and you can sketch some of these and check your work using Desmos. You're not going to hand it in or anything. Try these. Check your work using Desmos, right? So just make sure that once you've manipulated these, that you get the same thing that you did in Desmos. Okay. On that note, I'll stop. The day is yours, and I hope you have a great weekend. And thanks. I'm sure Shaun will let you know what's going on for Monday, but if you're still with me, we'll meet in here. If not, it's been a pleasure.
It's been a pleasure. And you'll be pleased to know I've signed up for your or calculus class next semester.
Oh, fun. Hey, that's awesome.
All right. See you around.
See ya.